Okay, welcome to this lecture video here for Material Science 410, where we'll be talking about X-ray photoelectron spectroscopy. This is some content for the Spring 21 session, which is specific to experiment number 3, looking at silicone diffraction gratings and characterization of such materials. In the secondary characterization exercise, XPS is used to understand the chemical composition of the cured silicone over top of a aluminum diffraction grating extracted from a compact disc. So the fundamentals of XPS date back to 1887, where the photoelectric effect was first studied by Heinrich Hertz. And in these early works, the exercise was simply to impose irradiation in the form of light onto various materials and to measure emitted electrons. And so the general architecture of the instrument is shown here at right, where incident light was imposed on a target material. So this was an anode, typically metals in the early work. And vacuum was applied to the chamber, and some distance away was the opposite material, a cathode, used for collecting any electrons ejected from that target anode material. As electrons imposed onto the cathode, the current was registered via the ammeter here, and so the remaining electronics, the voltmeter, and the battery were used to drive the voltage between these two plates, and thus experiment on sort of the relenting force that could be applied to electrons as they travel towards the cathode. So the main idea of X-ray photoelectron spectroscopy, or XPS, is to impose radiation onto materials again. So here we'll see that the appropriate energy is now in the form of X-rays, and we'll target any material, not just metals, and we will eject electrons from the atoms in that material, and these will travel to a detector for quantification. The technique is a high vacuum technique. We'll need electrons to travel towards a detector without being scattered off their mean free path. And high vacuum conditions work for this. And so that's why you see the instrument here outfitted with a lot of high vacuum hardware, vacuum pumps and pressure gauges, and of course X-ray source and X-ray and electron detectors. The plots are typically showing an intensity of detected electrons. Okay, so we have an intensity in kilocounts per second. So that's sort of events at the detector, impacts at the detector, in thousands of counts per second. And our x-axis is the binding energy of the electron. So how tightly held it was to a material. So we're going to be able to calculate this binding energy based on some known information for the energy of the incident X-ray and the work function of the material and the atoms in question, so the material. Okay, so what we get from an analysis like this is we get an elemental identification in the topmost layer of the material. The topmost layer of the material is on the order of 1 to 10 nanometers, depending on the material and the interaction volume for the X-rays and the escape range of those electrons from those atoms in that topmost area. Not only that, because we are measuring the amount of force that was holding those electrons in place, the binding energy, we're going to be able to understand the chemical state. So this is, for example, the oxidation state of the element. We can tell neutral iron from its rusted format, its iron oxides. And we'll be able to see that via a different intensity on that binding energy graph XPS spectra that we showed on the previous slide, for example. Okay, and so what we have here for the fundamentals is some material represented here by this energy graph showing all the electrons. So here we have 1s, 2s, 2p, 3s, etc. for all the energy levels of atomic orbitals. And you can see here that the incident X-ray, a photon with energy h nu, can be imposed onto the material, and we can eject an electron that was once part of an atom. This electron will leave the atom and have speed, which we will quantify and call kinetic energy, of course. And this gives us the ability to track the energy at which that electron was held in place originally. Okay, so a simple measurement of the difference in energy between kinetic energy and our incident energy from our X-ray will allow for that calculation. This signal is going to be unique to the type of atoms that are present, and this is going to allow us to quantify the type of atoms present, and this allows us to get the relative composition in that topmost layer of a material, again 1 to 10 nanometers. And as the diagram indicates, since we're probing at bonded electrons, we're probing at the valence band structure by doing so. So we're looking at bonded electrons, and we can even extract electrons from orbitals that are deeper than the topmost energy layer. So we can extract 2s and 1s electrons depending on the incident energy. Okay, so the fundamentals here, putting a little bit of mathematics to it, are that the energy of the emitted electron, the photoelectron we'll call it, is equal to the energy of the incident X-ray, so that's h nu, minus the binding energy that was holding that electron into its core level. Okay, so we'll show that here as E1. Okay, this is sometimes abbreviated E sub B, or in other equations simply BE as the acronym for binding energy. And the last piece we need to know is a correction factor, which is the minimum energy it takes to extract an electron from a material. It's a bit of a background feature here, and this will be the work function of the material. Okay, so these work function values can often be found by calibrating the instrument and applied to the mathematics quite easily. So the ability for us to calculate the energy of the electron, kinetic energy of the electron, the E photoelectron, simply means understanding the frequency of our X-ray and determining by difference the binding energy at which it was held, and knowing something about the instrument as well as the material, the work function. Okay, so here's an example to get us thinking about this. So to kind of rework that equation into a form that's perhaps a little more obvious, we've got some of the optional listings of the variables listed here. And we're going to show that the binding energy is equal to incident X-ray energy minus the kinetic energy minus the work function of the spectrometer. Okay, so here's an example where we have an XPS electron found to have a kinetic energy of 1055.3 electron volts. Okay, so this would be the EK value. Was ejected using an aluminum K alpha source of 0.83393 nanometers. Okay, so you can see that this is speaking to the incident X-ray energy. And we used a spectrometer that had a work function here of 25.1 electron volts. So that piece there is our W value. Because of where the signal occurred, we've looked at tabulated information, and we know that that's in line with a 1s electron being ejected from a nitrogen atom. And not only that, we've looked at literature and found that signal is very much indicative of sodium nitrate. So we can ask the question, what is the binding energy for the electron? And we'll use this in electron volts. Okay, so our solution here involves working some of the fundamental equations for energy and knowing some of the constants for that. So we're going to need Planck's constant for this. So our solution is going to make use of Planck's constant 6.626 times 10 to the minus 34 joule seconds. We're going to use the frequency of the radiation. Okay, so remember this is frequency of the X-ray. We've got the speed of light. That's going to come into our equations here. So again, this is 2.998 times 10 to the 8 meters per second. And we've got a conversion factor between SI units for energy, meaning 1 joule is known to be equal to 6.242 times 10 to the 18 electron volts. So that's a conversion factor between the electron volts and the joule. So our first step here will be to calculate the energy of the X-ray. All right, so hopefully you're remembering that we can do this provided we know some things about either frequency or wavelength for the radiation. So in this case, we're provided with the wavelength. And so we'll use the form E equals hc over lambda to help us with this. And so the numerator is the two constants, Planck's constant, 6.626 times 10 to the minus 34 joule seconds, times the speed of light, 2.998 times 10 to the 8 meters per second. And we have to divide that through by our wavelength in meters, given that we've used c, speed of light, with units of meters per second. Okay, so that's going to be 0.83393 times 10 to the minus 9 meters as an internal conversion from nanometers to meters, using a billion as a factor there. Okay, so in doing so, we find that the energy of this aluminum K alpha X-ray is 2.3799 1 times 10 to the minus 16 joules. Okay, we know that we're trying to use our XPS binding energy equation in electron volts, provide that binding energy in electron volts. So now would be a good time to convert this energy of the X-ray into electron volts. So we'll multiply by that conversion factor that we have here, putting joules in the denominator, and 6.242 times 10 to the 18 electron volts as our numerator. And this gives us the energy of the X-ray as 1485.53 electron volts. Good, first step. So at this point, we now know our first term, the energy of the X-rays. Okay, so this part is done. That's step 1. All right, step 2 is to simply solve for that equation given the rest of the info provided. So we were told that the kinetic energy found for the ejected electron was 1055.3 electron volts, and we were told that the work function value was 25.1 electron volts. So at this point, it's a simple subtraction to work this equation, and we can finally associate the binding energy here of this electron from the 1s. Okay, so 1485.53 electron volts minus 1055.3 electron volts minus 25.1 electron volts gives us a final answer here of 405.13 electron volts for this nitrogen 1s ejected electron. Okay, so this represents the energy in electron volts. We could use this equation to go backwards into joules, but regardless, it's the energy that is holding the electron in place. So we would be responsible for applying 405.1 electron volts if we need to eject an electron from nitrogen 1s having no kinetic energy. Okay, so going back to our graph earlier, this would tell us to expect nitrogen at around the 405.13 mark, and that's exactly where we see a nitrogen 1s typically in the binding energy versus intensity XPS curve.